I've mentioned different times this year that when we get to the complex number system, you will be able to take square roots of negative numbers. So today I'm going to introduce the complex number system. We'll be spending a few days in the complex number system, but this is just an introduction. And I want you to be able to define and use imaginary and complex numbers, and also to be able to solve quadratic equations with complex roots. So the first thing that we need to do is talk about what the imaginary unit is, and that is the square root of -1, and we use that to rewrite things. Remember, I talk about a lot of times math, you have to rewrite things in order to solve them. We're going to be doing some rewriting with complex numbers in this section. And a complex number is a number that can be written in the form a plus bi, where a and b are real numbers and I is the square root of -1. Okay, the set of real numbers are a subset of the complex numbers. Every complex number has a real part A and an imaginary part B. So if you look at this table, you'll see that the complex numbers are the entire set, and then real numbers and imaginary numbers are subsets of the complex number system. So real numbers are complex numbers where B equals 0. All right, let's simplify square roots of negative numbers. So what you need to do is you rewrite the negative square root, and you need to add root there, as a product of a real square root times the square root of -1. So if we look at this example over here, we have 2 times the square root of -36. We're going to rewrite the negative square root as a product of a real square root times the square root of -1. So all we do is we just rewrite this as the square root of +36 times the square root of -1. Because if I multiply those two square roots together, I'll get -36 underneath the square root sign. Okay, then you're going to simplify the real square root, and the square root of 36 is just 6. And then you're going to multiply the real numbers if applicable. And then we're going to express in terms of I. So the square root of -1, so I equals the square root of -1. So now when you have the square root of -1, you're going to replace it with I. So we'll multiply those two numbers together and we'll get 12i. All right, now we're going to solve a quadratic equation with just a quadratic term, so just an x squared term. So that is a little bit, or that's easier than when it has an x squared term and an x to the first power term, or a linear term. So we're going to first isolate the quadratic term. So this is our original problem, and we want to isolate the x squared term, so we're going to subtract 25 from both sides, and then it says to solve for x squared if applicable. Well, we need to solve for x squared because we have a 9 out in front that we're multiplying it by. So if we divide both sides by 9, then we're going to take the square root of both sides. So here, once we divide by 9, we get x squared equals -25 over 9. And when we take the square root of both sides, we can take the square root of the numerator and the square root of the denominator, and we have a negative number underneath the square root in the numerator. So what we're going to do is we're going to rewrite it square root of 25, square root of -1 over the square root of 9. And then square root of 25 is just going to turn into 5. This is going to turn into I, and it's going to be over 3. Now, when you write this, you want to write the I, so 5i over the square root of 3, and because we took the square root, we need to say plus or minus. So that's your final solution. Okay, now we're going to equate complex numbers. Now this looks really complicated, but it's really pretty easy. Two complex numbers are equal if and only if their real parts, so A, are equal and their imaginary parts are equal. So when you're looking at a complex number, here are this would be considered your real part, this is your imaginary part. Okay, so find the values of x and y that make the equation true. Now, because you haven't worked with I before, this might look like it's really complicated, but it's not. And what this says is we want to go to the real part, which means the part that doesn't have an I has to be equal to the part on the other side that doesn't have an I. So we want to get the parts that don't have imaginary numbers, put them equal, and then the parts that do have imaginary numbers, and put those equal. So here we'll have 2x equals negative 8, that's the real, and negative 6i plus 20yi, that's the imaginary. Okay, now, pretty easy to solve, or you should know how to solve 2x equals negative 8. You just divide by 2 on both sides, and you end up with x equals negative 4. Okay, and now we want to solve for y. So I just circled this y. What I need to get rid of is multiplying by 20 and multiplying by I. So I'm going to divide both sides by 20i. And when I do that, this turns into 1. This turns into 1. So now I have negative 6i over 20i. Well, I divided by I is 1. And then we end up with and then, oh, I forgot that I wrote this here. 20 divided by 20 is just 1. I divided by I is just 1. So we have y by itself, and it's going to equal, when I reduce the fraction, it's going to equal negative 3 over 10. So that's all you have to do. Set the real parts equal, the imaginary parts equal, and then solve for each. Okay, now we want, here's one for you to try to find the values of x and y that make that equation true. All right, on the other side, we want to find complex zeros of quadratic functions. So the first thing you're going to do is set the equation equal to 0. And we have that right here. And then you're going to rewrite by completing the square. So this quadratic is not factorable. So what you're going to have to do is subtract 13 from both sides. And then you're going to make a blank to complete the square. So we're going to divide 4 by 2 and square it. That's going to give us 4. It has to be added to both sides. So make sure, this 4 got off a little bit here, off the blank. Make sure to add 4 to both sides. Okay, and then in section 5.4, we just completed the square by taking the square root of the first term, square root of the last term, and then we can write a binomial squared, which is x plus 2 squared, and that's going to equal negative 9. Okay, now we can take the square root of both sides, and when we do that, we're going to have the square root of negative 9 over here. So I'm just going to rewrite that as plus or minus the square root of 9 times the square root of negative 1, and that's going to give us, we're going to change this to an I, and this square root of 9 is just 3. So we have plus or minus 3i, and then we just need to move that 2 over, so we're going to subtract 2 from both sides, and we have negative 2 plus or minus 3i. And that's your answer. Okay, complex conjugates we are going to use more in the section where we're dividing, but they introduce it in section 5.5, so we'll just talk about that real quick. Complex conjugates sound like it's something that's complex, but really very easy. You can find the complex conjugate of any complex number by taking the opposite of the imaginary part. If a quadratic equation with real coefficients has non-real roots, then those roots are complex conjugates. Okay, so example. This is all you need to do. You need to take the opposite of I, the I term, and write that I term last. So let's look at a couple of examples here. We have 2 minus 8i. I'm going to take the opposite of this and write it last. Well, it's already at last, so that's pretty easy to do. So it's just 2 plus 8i. So don't try to make it any harder than that. It's just very simple to do. We take the opposite of I and write the I last. Okay, this one, I'm taking the opposite of I. A lot of times people will tell me that this is 7i plus 4. That's not correct. You always take the opposite of the imaginary part of the number. So we're going to take the opposite of 7i, which makes it negative 7i, and then we subtract 4. But now we have to write the I term last, or the imaginary part last, so we're going to write 4 minus 7i. Now, if you have numbers that look like this, we just have an I here, so you're going to just take the opposite of the I. So it's going to be negative 12I and 6I. So again, we won't be using those until we start doing division with complex numbers, but they're introduced in this section, so I did want to go over them. Okay, you have a few questions to try on your own.